In-text question 6.4. Among the isomeric alkanes of molecular formula C5H12, identify the one that on photochemical chlorination yields. First one, a single monochloride. Second one, 3 isomeric monochloride. And third one, 4 isomeric monochlorides. First of all, what is photochemical chlorination? For example, if methane reacts with chlorine in the presence of light, then chlorine breaks into chlorine-free radicals, and this chlorine-free radical will substitute one of the hydrogens of methane, forming methyl chloride or chloromethane. So this is known as photochemical chlorination, where one of the hydrogens of methane is getting substituted by chlorine, or in general hydrogen of alkane gets substituted by chlorine in the presence of light. This is known as photochemical chlorination. Now in this question it has been asked that the compound C5H12, alkane having formula C5H12, that is pentane, which of the isomers of pentane will form first one, a single monochloride? Now the answer to the first one is this compound, this isomer of pentane, that is its IUPAC name will be, this is the longest carbon-carbon chain and numbering the chain as 1, 2, 3. This is 2,2-dimethyl propane. In this isomer of pentane, the second carbon, this is the quaternary carbon, and the other carbons which are present as methyl group, all these carbons are primary carbon. The quaternary carbon, it does not have any hydrogen atom, so it will not form bond with chlorine. Whereas the 4 methyl groups which are present around this quaternary carbon, the hydrogen present in these methyl groups may get substituted by chlorine, giving a monochloride. Now here this is one of the products formed. Now if you name this product, then this is the longest chain containing the chlorine atom, numbering the chain giving the lowest locator number to the carbon bonded to chlorine. So this becomes 1, 2, 3. The product is 1-chloro-2,2-dimethyl propane. Now similarly, if this carbon gets bonded to chlorine, then again this will be the longest chain and the numbering will be done giving the lowest locator number to the carbon bonded to chlorine. So 1, 2, and this will become the third carbon. Again the carbon bonded to chlorine gets the locator number 1. Similarly for this carbon also, when it gets bonded to chlorine, it will get the locator number 1. Then this carbon also, when it bonds with chlorine, it gets the lowest locator number as 1. So only one product, one monochloride is possible with this isomer. This isomer reacts with chlorine to give a single monochloride. So this is the structure of the isomer giving a single monochloride. Now the second part, 3 isomeric monochlorides. For 3 isomeric monochlorides, you will need 3 types of carbon atom, which when bond to chlorine give 3 types of product. Now this is the primary carbon, this is the secondary carbon. Then this is also secondary carbon, this is secondary carbon, this is primary carbon. Now numbering the chain from right to left, this is 1, 2, 3, 4, 5, and numbering the chain from left to right, this will be 1, 2, 3, 4, 5. Now as can be seen, the lowest locator number for the carbon present on the right end of the chain is 1, and the lowest locator number for the carbon present on the left end of the chain is 1. So these two carbons are of the same type. So denote these carbons by the alphabet A. Now again, from the right hand side of the chain, this is the second carbon, and from the left hand side of the chain, this one is also the second carbon. So these two carbons are also same. So name them as carbon B. And the third carbon, it has the same locator number, that is 3. So name this carbon as carbon C. So as can be seen, there are 3 types of carbon present in the chain. So 3 types of chlorides will be formed. When carbon number 1 is bonded to chlorine, it is 1-chloropentane because the longest carbon-carbon chain is of 5 carbon. When carbon number 2 is bonded to chlorine, then it is 2-chloropentane, and when carbon number 3 is bonded to chlorine, it is 3-chloropentane. Now the third question, 4 isomeric monochlorides. 4 isomeric monochlorides. For that 4 different types of carbon will be required. Now here in this compound, in this isomer, this is the primary carbon, this is the tertiary carbon, this is the secondary carbon, this is again the primary carbon. A methyl branch is present on this carbon chain. So the longest chain will be selected and locator number will be given to the chain so that carbon containing the methyl group gets the lowest locator number. Now if chlorine bonds to this carbon, then numbering the chain, this will be carbon number 1, this will be 2, this will be 3, this will be 4. The product will be 1-chloro-2-methyl butane. If chlorine is bonded to this carbon, that is the tertiary carbon, then the product will be 2-chloro-2-methyl butane. Again, if the chlorine is bonded to this secondary carbon, to give the lower locator number to chlorine, carbon bonded to chlorine, the chain will be numbered from left to right, that is 1, 2, 3, 4. Now the name of the compound is 2-chloro-3-methyl butane, and when chlorine is bonded to this carbon, then the name of the compound is 1-chloro-3-methyl butane. So 4 different isomeric monochlorides are formed. So if you want only a single monochloride, then you have to arrange the carbon-carbon chain in such a way that there is only one type of carbon present. So no matter to which carbon chlorine is getting bonded, the product will be the same. If you want 3 isomeric monochlorides, in that case carbon-carbon chain has to be arranged so that 3 different carbons are available, and so that 3 different products will also be formed. 3 different monochlorides will be formed. For 4 isomeric monochlorides, carbon-carbon chain has to be arranged so that 4 different carbons are available, and when chlorine bonds to these 4 different carbon atoms, it gives 4 different monochlorides. These monochlorides, they have the same molecular formula but different structures. Physical properties. Alkyl halides, any alkyl halide, when it is pure, it is colorless. But bromides and iodides, when exposed to light, they develop a deep color. Then alkyl halides, which are volatile, means which can go into the vapor state easily, they have a sweet smell. Now melting and boiling points. Usually the methyl chloride, methyl bromide, ethyl chloride and some chlorofluoromethanes are gases at room temperature. But higher members are either liquids or solids. Now as compared to the alkane, suppose methane and methyl chloride. In comparison to methane, the molecular mass of methyl chloride will be higher. In case of methyl chloride, there is a bond polarity because the carbon chlorine bond, due to the greater electronegativity of chlorine atom, develops a polarity. So the bond is polar, because of which there is dipole-dipole interaction. So in comparison to the alkane, the alkyl halide containing the same number of carbon atom, the intermolecular forces of attraction are stronger in halogen derivatives. So due to the greater bond polarity, due to the higher molecular mass, greater bond polarity as well as higher molecular mass compared to the parent hydrocarbon, the intermolecular forces of attraction. Now in case of alkyl halide, there are dipole-dipole interactions as well as van der Waals interactions. So these are stronger in halogen derivatives. So in comparison to the hydrocarbon from which these alkyl halides are derived, The boiling points of chlorides, bromides and iodides are higher than those of hydrocarbons of comparable molecular mass. Now in this graph, the boiling point of chloride, bromide and iodide of different alkyl halides is shown. So in case of derivatives of methane, now as can be seen for the same alkyl group, the iodides have higher boiling point than bromide, bromide has higher boiling point than chloride. So iodide has a higher boiling point than bromide, bromide has higher boiling point than chloride, chloride has higher boiling point than fluoride. What is the reason? The reason is with increase in size and mass of halogen atom, size of iodide is greater than bromide, which is greater than chloride. Size of iodine is greater than bromine, which is in turn greater than chlorine. So with increase in size and mass of halogen atom, the van der Waals forces also increase. And with the increase in the van der Waals forces, boiling point also increases. So these alkyl halides, they can exist in gaseous state as well as liquid state as well as solid state. The alkyl halides are polar. In comparison to the alkane from which these alkyl halides are derived, the molecular mass of alkyl halides is higher. Due to bond polarity, they have two types of attractive forces, that is, first one is dipole-dipole interaction, second one is van der Waals interaction. Due to higher intermolecular forces of attraction, their boiling points are higher than those of the hydrocarbons of comparable molecular mass. Iodides have higher boiling point than bromide, bromides have higher boiling point than chloride. Reason being, iodides, due to their higher molecular mass, greater size of the halogen atom, the van der Waals forces are also high. So with increase in the size and mass of the halogen atom, van der Waals force increase and the boiling point also increases. Now boiling point of isomeric haloalkanes. As you can see, this is normal haloalkane. This haloalkane has one branch and this one has two branches. One is methyl and another one is due to bromine present on the tertiary carbon atom. It can be seen that with increase in branching, boiling point decreases. The one having maximum number of branches is having the minimum boiling point. So what is the reason behind decrease in the boiling point due to branching? Due to branching, the effective surface area decreases. The molecule assumes more or less spherical shape, so effective surface area decreases, as a result of which the van der Waals forces of attraction decrease and boiling point also decrease. Next is boiling point of isomeric dihalobenzene. Now as can be seen, the boiling point and melting point of ortho dihaloderivatives and meta dihaloderivatives are almost the same. In case of para isomer, the boiling point is almost the same as the ortho and meta isomers, but the melting point, as can be seen, in comparison to the ortho isomer and meta isomer, the melting point of the para isomer is high. What is the reason behind this high melting point of para isomer? The para isomer molecule is symmetrical, and due to the symmetry of para isomers, it fits in the crystal lattice better as compared to ortho and meta isomer. Due to the symmetry, it fits into the crystal lattice better than the ortho and the meta isomer, as a result of which its melting point increases. Then comparison of density. Bromo, iodo and polychloro derivatives of hydrocarbons, they are always heavier than water. Density will increase with increase in, first one is number of carbon atoms, second is the number of halogen atoms, third is the atomic mass of halogen atom. Now in this table, as can be seen, this is chloropropane, this is bromopropane and this is iodopropane. the density of iodo-propane is the highest. Means as the atomic weight of halogen atom increases, density increases. Next is, this is dichloromethane, this is trichloromethane, and this is tetrachloromethane. Density of tetrachloromethane is the highest. Means with increase in the number of halogen atoms, density increases. Next is solubility. Haloalkanes are very slightly soluble in water. What is the reason? Now water molecules, they are held together by hydrogen bonds. So there is hydrogen bonding between water molecules. As far as haloalkanes are concerned, haloalkane molecules are held together by van der Waals forces, and they are also having dipole-dipole interactions. So the two kinds of attractive forces present in the haloalkanes is van der Waals attraction and dipole-dipole attraction. Now, when haloalkane is dissolved in water, the hydrogen bond between the water molecules has to be broken, and energy is also required to overcome the attractive force between the molecules of the haloalkanes. Then, if haloalkane dissolves in water, there has to be some interaction between the haloalkane molecule and the water molecule. Now, whatever is the energy released when the haloalkane molecule interacts with water molecule is less than the energy required to break the hydrogen bond between water molecules and to overcome the attractive forces between the haloalkane molecules. As a result of which, the solubility of haloalkanes in water is less. So here it is written, in order to dissolve haloalkane in water, energy is required to overcome the attractions between the haloalkane molecules. These are the dipole-dipole attractions and van der Waals attraction, and break the hydrogen bonds between the water molecules. Less energy is released when new attractions are set up between haloalkane and the water molecules, and these are not as strong as the original hydrogen bonds in water. So solubility of haloalkanes in water is low. But when haloalkanes are dissolved in organic solvents, the new intermolecular attractions between the haloalkane and solvent molecules, they have the same strength as the ones being broken in the separate haloalkane and solvent molecules. So they have the same strength, means whatever energy is required to break the interactions between the solvent molecule and the haloalkane molecules when they are separate is more or less same as the energy released when the haloalkane molecule interacts with the solvent molecule. So in this case, haloalkane molecules are soluble in organic solvents, because energy released when haloalkane is dissolved in organic solvent is almost same as the energy required to break or overcome the interaction between the haloalkane molecule and the interaction between the solvent molecules. Now next is a question. Arrange each set of compounds in order of increasing boiling points. This is bromomethane, then bromoform, then chloromethane, then dibromomethane. So formula will be, bromomethane will be CH3Br, bromoform will be CHBr3, then chloromethane will be CH3Cl, and dibromomethane will be CH2Br2. Now minimum boiling point will be of chloromethane, and then next is the boiling point of bromomethane. Then boiling point of dibromomethane will be higher than bromomethane, and boiling point of bromoform, that is CHBr3, is the highest. This is the answer to the first question. Next is 1-chloropropane, then isopropyl chloride, and 1-chlorobutane. Isopropyl chloride will have the minimum boiling point, then 1 chloropropane, and the highest boiling point will be 1 chlorobutane. So isopropyl chloride has the lowest boiling point, then 1 chloropropane because only 3 carbon atoms, and then 1 chlorobutane. In 1 chlorobutane there are 4 carbon atoms, so maximum boiling point. 1 chloropropane, 3 carbon atoms, and these are the straight chain compounds. 1 chloropropane and 1 chlorobutane are straight chain compound. Isopropyl chloride, this compound has a branch, so it has the minimum boiling point. Chemical reactions. Chemical reactions shown by haloalkanes are: first one, nucleophilic substitution; second, elimination; third, reaction with metals. Now, nucleophilic substitution reaction. What is a nucleophile? Nucleophile means nucleus seeking. It is denoted by Nu, and since it is nucleus seeking and a nucleus is positively charged, means nucleophile has negative charge on it, or it is electron rich species. So this is how the nucleophile is denoted, and this nucleophile, it will form bond with the positive end of the substrate. Substrate means here alkyl halide is the substrate. When nucleophile reacts with alkyl halide is termed as substrate. Carbon halogen bond of alkyl halide is polarized. The carbon contains slight positive charge and the halogen atom contains slight negative charge. Nucleophile will form bond with the positive end, means it will form bond with the positively charged carbon, and halogen atom leaves as halide ion. So the product formed is, now instead of halogen, the carbon of the alkyl halide is bonded to the nucleophile and halogen leaves as the halide ion, and this is also known as the leaving group. So leaving group is halide ion. Now this substitution reaction is initiated by the nucleophile. It is called nucleophilic substitution reaction. The carbon which is bonded to halogen atom is sp3 hybridized. This carbon is sp3 hybridized. So if this is the carbon bonded to halogen, the bond is polarized. Halogen atom has slight negative charge, carbon has slight positive charge. Nucleophile, which is rich in electrons, will form bond with the positively charged carbon. Halogen atom leaves as halide ion. This kind of reaction is called nucleophilic substitution reaction. And this alkyl halide is known as the substrate. Nucleophilic substitution reaction can be defined as the reaction in which a nucleophile replaces already existing nucleophile in a molecule is called nucleophilic substitution reaction. This halide ion is also rich in electrons, so this can also be called a nucleophile. So a given nucleophile is replacing the already existing nucleophile. So this is known as the nucleophilic substitution reaction. Now here this is a table showing different types of nucleophile and the substitution products formed. This is the alkyl halide, this is the nucleophile, this is the substitution product formed. So if the nucleophile is hydroxide ion, the product formed is alcohol. Nucleophile is water, then also product formed is alcohol. If the nucleophile is alkoxide ion, then the product formed is ether. Then nucleophile is iodide ion, then product is alkyl iodide. With ammonia, the product formed is primary amine. With primary amine, the product formed is secondary amine. With secondary amine, the product formed is tertiary amine. When the reaction takes place with KCN, when the reagent is KCN, nucleophile is Cn minus, where the negative charge is on the carbon atom. So product formed is cyanide or nitrile, alkyl cyanide or nitrile. When the reagent is AgCN, then the nucleophile which is generated, then nitrogen acts as the nucleophile. So carbon forms bond with the nitrogen atom of the CN group and the product formed is isocyanide or isonitrile. With KNO2, alkyl nitrite is formed. With AgNO2, nitroalkane is formed. What is the difference between these two products? In case of nitrite, in case of alkyl nitrite that is formed, the carbon atom of the alkyl halide is bonded to the oxygen atom of the NO2 group. And in the nitroalkane that is formed, the carbon atom of the alkyl halide is bonded to the nitrogen of the NO2 group. So, silver nitrite will form nitroalkane, whereas potassium nitrite will form alkyl nitrite. Then, with the salt of the acid, this is the carboxylate ion, ester will be formed. With lithium aluminum hydride, there will be the halogen will be replaced by hydrogen and alkane will be formed. Now, with reagents like Grignard reagent, for example RMgX, this will generate an alkyl group having negative charge. So, alkyl group with negative charge acts as nucleophile and the product formed is an alkene.